Hi guys, we're going to learn about something in a circle called a tangent line. We're also going to learn about these awesome other nifty lines that go through circles as well as segments. But predominantly, we're going to be focusing on properties of tangent lines with circles, so get excited. Alright, so before we talk about tangent lines specifically, we need to discuss what all these nifty lines and segments are that go through a circle, because don't they look exciting? I know, I agree. All right, so the first thing that we've actually already talked about is called the radius. So the radius of a circle, it is a segment that starts from the center point and extends to a side of a circle. Okay, so a segment whose endpoints are the center and a point on the circle. Okay, and every single radius in a circle, okay, all of them are going to be congruent. So the lengths of all the segments are actually equal in length. So that's pretty cool, right? Something else to keep in mind is the radius is half the length of the diameter, which you're probably like, Miss Long, well, what's a diameter? Don't you worry, I'm about to tell you. Okay, so a diameter is a segment in the circle that starts from one end of the circle, hits the center point, and then bam, hits the other side of the circle. So it's a segment that contains the center point and has two endpoints on the circle. So a diameter has to hit the center. If it doesn't hit the center, it's going to be considered a different segment, which we'll talk about in a moment. Okay, so a diameter is broken down into two radii. Radii is plural for radius. Sounds cool, right? Try saying radii 5 times as fast as you can. Radii, 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 radii. Cool. All right, so a diameter is broken up into two radii. So like each diameter has two radii in it. So the radius is half the length of the diameter. So if you know the diameter's length, if you divide that bad boy by 2, bam, you get the radius. Also, the reverse is true. If you double the length of the radius, since there are two radii in a diameter, you will get the diameter. Cool beans, right? I know, let's keep going. All right, let's talk about these other awesome segments and lines that go through the circle, which I know you've been dying to learn about during the start of the Prezi. I know you've been wanting to learn about them this whole time, so I'm about to tell you. Okay, so the next segment we're going to talk about is something called a chord. Guys, and a chord is a segment whose endpoints simply have to be on the circle. Okay, so chords do not have to contain the center. Now, they can contain the center, but they don't have to. So a diameter is a very specific type of chord. Okay, so all diameters are chords, but not all chords are diameters, so be careful. Okay, this line right here, which is similar to a chord, it's a line, it's called a secant. A secant is a line that intersects the circle in two nifty points. So it slices through the circle and hits in 2 points. Like this one hits it right there, bam, and right there. Okay, so within a secant line, there is a chord, because if you take the segment from here to here, guess what? Both of those endpoints are on the circle, which means that's a chord. So chords are within secants. So secants have to be a line, chords have to be a segment, so watch yourself. Guys, and the last nifty line we're going to talk about is a tangent line. So a tangent line, it is a line that only hits the that only hits the circle in exactly 1 point. So like this line's coming along and bam, it hits it once and keeps going. Guys, so secants have to cross through the circle and have to hit the circle twice. Tangent lines never cross through the circle at all. They just hit the edge of the circle and they only hit the circle in 1 point. Okay, so tangent things never cross through something and they always hit something in 1 point. Okay, so there can be tangent lines, there can be tangent circles, there can be tangent figures. Okay, we've also talked about graphs that have points of tangency where they only hit the x-axis in one spot and they don't cross through. So tangent lines simply just mean they have to hit something in exactly 1 point, which there's many variations of points of tangency and tangents. Okay, not just lines, which we'll see in a moment. Guys, so a point of tangency, it is the point where the tangent line and the circle intersect. Kind of straightforward. So like this tangent line's coming like this, and then bam, it's in that point. So that is the point of tangency, and this is the tangent line. So be careful, they are different. Guys, and then these are circles that are tangent to each other because they only hit each other in one point. So these two circles are internally tangent, which internal means to be within something. So internally tangent circles are two circles that lie within each other and intersect in exactly one point. So these two circles intersect right here. Bam. And the tangent line also hits the point right here. So this is a point of tangency for tangent circles and for the tangent line. Cool beans, right? I know, I know. Guys, now these two circles are externally tangent, which external means to touch, or external means to be on the outside. So these circles are touching outside of each other, and they still touch in exactly one point. Bam, right there. Okay, so there are two circles that are adjacent, which means they're next to each other, and intersect in exactly one nifty point. So these two circles are tangent to each other, as well as this is a tangent line, because they're all hitting exactly one point. Cool, right? All right, let's keep going. Guys, so we're going to be using those properties of internally tangent circles and external tangent circles, and we will be identifying the length of the radius, which we're simply going to get by counting the spaces from the radius to the edge of the circle. Okay, we're going to identify the point of tangency where the circles and the line intersect in exactly one point, and we're going to write the equation of the tangent line. Okay, so in this one we have a horizontal tangent line. On this one we have a vertical tangent line, which horizontal and vertical lines are written much differently. So horizontal, you want to think of horizontal because it's a y equals line, and it's a y equals wherever it smacks the x-axis. So wherever the line hits the x-axis, that's what your y equals equation equals. Okay, the reverse is true with a vertical line. So vertical lines think vertical because it's an x equals equation. Okay, and it's going to be x equals wherever this line smacks the x-axis. So that is how we will be making our vertical line equation. So get excited. Oh yeah, go ahead and pause the video and watch example 1 and 2. This is a funsie, which we'll get to later on. Don't you worry, I pinky promise. Alright, so guess what? We have even more properties to discuss. Guys, so if a radius intersects with a tangent line, okay, the point of tangency is right here. So if a radius and tangent line intersect at the point of tangency, that means the radius and the tangent line are perpendicular, which guess what, you guys? That means they form a right angle. So if a line is tangent to a circle, then the radius is perpendicular to the point of tangency. So if you draw a radius to the point of tangency, bam, it's perpendicular, which means a right angle forms. And the reverse of this statement is also true. If a tangent line is if a tangent line is perpendicular to a segment, then the segment has to be the radius or the diameter. So if you don't know what the segment is and it's perpendicular to a tangent line, that has to mean it's a radius or diameter. So keep that in mind. So we're going to be using these properties to solve example 3 and 4, which if you notice, there are tangent lines intersecting with a radius, okay? This one has two tangent lines right here and right here. Okay, and the radius is touching this point of tangency as well as that one. So there's going to be lots of right angles that are forming, so get super pumped up. Alright, so go ahead and pause the video and watch example 3 and 4. Okay, and then example 5 and 6, we're still applying this rule where if a radius touches a point of tangency, right angles form. So we're going to be using that same property as an extension to kind of step it up a notch because these last two just weren't hard enough, right? So we gotta make the problem more challenging. The more challenging the problems, the more exciting. So go ahead and pause the video and watch example 5 and 6. Alright guys, so we have one more tangent property for you. I know you've been wanting to learn about all the tangent properties, so this is the final one. Okay, so if you have two tangent segments that intersect in the same external point, like segment FH and segment JH, both intersect at point H, If that's the case, if you have two tangent lines that intersect in the same external point, so a point outside the circle, that means that the tangent lines are congruent. So JH is congruent to FH. Guys, so if two segments are tangent to a circle from the same external point, guess what? Then the segments are congruent. Okay, so we're going to be applying this property in examples 7 and 8 because if you guys see, there are so many tangent segments. We got this one's a tangent segment, AH. GH is one, GF, FE, ED, DC, CB, and BA. So there's lots of tangent segments that are intersecting in the same external point, which means we're going to have several congruent segments, several congruent segments. But I don't want to give any more away because it will spoil the fun of example 7 and 8. So go ahead and pause the video and watch example 7 and 8. Guess what, you guys? That's all, folks.